I'm Ofer from Taboola. I'm going to talk about deep learning approach to content recommendation system. So you've seen us before. This is an example of the Taboola widget that we display in many sites. It's basically content recommendation company. A little bit about the numbers, just to understand the huge scale. So, for example, we have more than 50 billion recommendations a day. We have almost 1 billion monthly unique users. We once looked at our database and realized that we have more unique users than people on Earth. So it's a lot of users. Obviously, it's a cookie issue, but the scale is still huge. I'm first going to talk about the problem and the challenges, and then going to the solution, the model evolution, and finally, deep learning. So the problem is very simple to describe. A user comes to a site, to a specific page, and we need to find the best recommendation that maximizes either the click-through rate or the revenue. We have to choose it from over 1 million possible recommendations. Though it's very simple to describe, this is a very complex problem. We have to do it in very short time, less than a second, rank all the possible recommendations, and then choose the best ones. The input to the algorithm is obviously the recommendation. So we have the titles and the thumbnails and other metadata features about the items. We have context metadata like browser and platform. We have location-based information, and we have the user historical data, his historical preferences, things that he likes, and more important, things that he doesn't like. And the output of the algorithm is the recommendations. A little bit about the challenges. The first challenge is the data is very sparse, which implies many weights to the model. If we take, for example, advertiser feature, we have more than thousands of advertisers. So the data is very sparse. The data is very noisy. We have inconsistencies in the data. Many new items arrive every day, and many other sources of noises. Cold start is a big challenge. We can either have a very cold start, users that we have never seen before, items that we have never seen before, or we can have semi-cold that is cold for this situation. Specific situation, I will get to it later. And of course, the huge scale, which is a problem everywhere. How to store huge amount of data, how to retrieve it, how to train a model in a feasible way, how to serve very quickly. So we start with the horse work of machine learning and statistics. These are the linear model, logistic regression. They are very appealing because they are very simple, very easy to train, very easy to serve with. And they are also understandable. The weights of the model actually mean something. But unfortunately, they are too simple, and we cannot use it as is. Data in the real world is hardly linear. So if we want still to use linear models and to get the benefits, we need to first break the linearity in linear models. One technique doing that is to bucket every numerical feature into intervals. Each interval get its own weight. So it increases the number of weights, but it breaks the linearity. Another technique is do Cartesian product of features and get to higher level polynomials. Another problem with linear models is the sparsity problem. If we take, for example, again, let's take the advertise feature, which in linear models is usually a model. The model of categorical features is one-hot encoded vectors, and we take the Cartesian product of the advertiser with, say, for example, publisher, we get 1 million length vector, which is very sparse. So we need what I'm calling bag of tricks in order to reduce the dimensionality, eliminated unfrequent data points from the data set, hashing trick in order to reduce the dimensionality of the vectors. So after breaking the linearity and the bag of tricks of reduce the cardinality, linear models are very powerful and for this problem. The next that I'm going to talk about is the matrix factorization. In machine learning, we always talk about features and how important it is to find the most interesting features. The beauty in matrix factorization is that there are no features. The machine learning itself finds the features. It's called latent features. So again, with the cold start problem, in many cases, we can borrow strength from points with a lot of data to a point that we have no data. Let's take, for example, items that we presented on MSN many times, but we have never presented it on USA Today. But if we know that MSN and USA Today are similar publishers, then we can conclude about the behavior of this item also in USA Today. The reason that we know that MSN and USA Today are similar publisher, it's because their latent vector are closed in the space. And the way to do it is by matrix factorization that give each feature a latent vector. And then the regression result is just the dot product of the two latent vectors. So the input to the matrix factorization is a sparse matrix with partial data. And after we have the latent vector, we can fill the entire matrix with data. And the reason this is so appealing for our problem is that we have in many pairs in which we can borrow strength for the data is very hierarchical. For example, we have the publisher to items that I just described, publisher to advertiser, user to item, and so on. If linear models and matrix factorization are so powerful, why go deep? So first reason is that there are several hard problems, sub-problems, that is very appealing to solve with deep learning. For example, NLP problems and text modeling. In the picture, you can see a network for attention modeling from our titles modeling. The second reason is that we have many matrix factorization pairs, but eventually we want one model end-to-end to learn all the connections. And the third, that we want also to reveal deep connections which are beyond the pairs. So deep learning. Deep learning has many meanings. We chose the solution of generalized matrix factorization. So for each categorical feature, we have embedding, which represents the latent feature from the, we borrow the concept from matrix factorization. We also have many numerical features. And then we have a deep neural network that produces the CTR. Neural network, although we assume that it can simulate any function, simply put all the models in one big container and then build many layers on top of it wouldn't work. It's not feasible. The network will be too big. It will not be feasible to train, to serve. It will be difficult to do hyperparameter tuning. So the way we decided to build our network is to build subnetwork. Each subnetwork has its own goal. So for example, in the picture you see that we have a subnet for item modeling, item features, subnet for user, for context, and then we build on top of it another sub-neural network that captures the connection between them and then produces CTR. Now let's revisit the challenges and see how deep learning answer it. So regarding the sparsity, as opposed to linear models, we are no longer with one huge one-hot encoded vector. We use embedding of this specific value of the categorical feature. Regarding the noisy data set, we use out-of-vocabulary injections, so we will not be surprised from new examples. Regarding the cold start, I mentioned the concepts of matrix factorization. And regarding the nonlinearity, we use neural network in order to catch the deeper connections. Neural networks are often considered as black boxes. This is one disadvantage comparing to linear models. But actually, in deep learning, we can shed some light on these black boxes. The way we build our network with the structure that each sub-network has its own goal make it easier to debug and understand what the network is doing. Similar items should have similar embeddings, similar weights, so we can understand if each model doing its work. For example, this is the embedding space for our word embedding of our title modeling. So we can see that the vector of Messi is next to the vector of Pelé and Ronaldinho and other players. So we can understand and get the feeling that the model is doing what it's supposed to do. Deep learning is very good at generalization, but because of the noisy data set and the nature of the problem, we also have many exceptions, which deep learning is not good at, but linear models are. The reason that linear models are good at exceptions is that they're just memorizing the data, and we have specific weight for each Cartesian product, for example, of features. So in this sense, linear are very powerful. One solution is to combine and to enjoy both worlds. So the deep network will generalize, and hopefully the linear model will catch the exception. They will be unified with one loss function, and we can enjoy both. Another big challenges in recommendation system, Joseph talked about it in his lecture, is in order to do efficient machine learning, we need efficient offline measures because we want to do it fast iteration. But there are several differences between the offline and the real world. For example, one example is improving the CTR prediction doesn't necessarily improving the ranking. For example, I can take a very appealing user feature, improve all our CTR prediction, our offline measures will look much better, but we didn't change the ranking, so we will not earn more money. Another source of difference is the difference between optimizing the CTR prediction and not optimizing the entire list revenue, list of recommendation. Or more ambitious goal is to optimize the entire session of the user. And more ambitious goal is to optimize a long-term revenue. And this is also the engagement of users and much more complicated problems to optimize. Okay, before the end, I just want to mention several other projects that we do in Taboola. So we have the exploration exploitation. Trade-off exploration is revealing new items that we have never seen before. We do title modeling using LSTM, a recurrent neural network, in order to capture the sequence of data. We do attention modeling also for title modeling, thumbnail modeling using convolution neural networks, and many other tasks that I didn't mention. That's it. Questions?